So we are going. Uh, we are here to talk about device tree migration from Linux kernel into U-boot. You might have noticed a lot of discussions happening in the mailing list about device tree sync. Now, keep in mind, this recording we're going to put it in YouTube.
Okay.
Yay! All right. So, um, where do I get started? All right. So, device trees. So, split tree. I'm just going to split my screen so that you guys can see what I'm doing. And I will make a lot of mistakes on the way. So, so, okay. Let me first introduce you to a few prerequisites projects. Since building device tree, now some of this content is just purely TI stuff, so may not be that interesting, but we will get to the interesting part. So building U-boot, especially for TI platforms, tends to be a little bit of a pain in the butt because you have to build ARM trusted firmware, uh, Opti operating system, and you need different pieces of these firmwares to all come together for the base system to boot. Now, which is very fortunate since we just updated a few minutes back a pull request in U-boot mainline to clean up our documentation, and it'll get into the master branch very soon. But here is the generator documentation about this. So overall system boot flow, and this is exactly why we wanted to do this session, because my friend here, Reed,
Hi.
we are not on camera, are we? Wanted to understand. So he's a Linux kernel developer. He's trying to help on U-boot, and he's trying to figure out what exactly the different pieces in U-boot need to be. So good news, we have documentation. And we realized that we need documentation even for ourselves to figure out how the hell this thing works. Um, I'm sorry. One second while I stop my notifications. Done. So, so this guy involves multiple processors. That's the entire device. K3 architecture devices all follow the same. We have a very high level documentation that we have written, which actually starts walking you through the basic processes. ROM gives control to a SPL, which in turn gives control to trusted firmware application, Opti, and then there is yet another SPL that comes into play on the main domain side. Finally, U-boot a Linux kernel comes into play. Most of the folks are aware of boot from, oh, I see a U-boot shell, I see a Linux shell. This is where most of the folks are kind of living their life. The black art is on the left side of the story. And this is where we go into a little more details. There are many more deep dive details that we go into, but we will pick J721E as an interesting platform. So, or rather 6.2 as an interesting platform because I'm about to show you the demo of 6.2. So, if you just go to the U-boot documentation once all of our stuff is merged and you just search for AM62, padang! First link! Yay! It works! It gives you some details as to what the chip is, blah blah blah. But for our discussion here, this is the picture that is going to be very interesting. We kind of spoke about a little bit about ROM handing over to SPL, then jumping back, jumping forward. So a little bit of a dance that goes into play. A couple of firmwares that come into play is the TIFS firmware and the device management firmware. Okay. Now TIFS firmware, unfortunately, due to let's say legal requirements slash other requirements, we have to encrypt it, and the sources are not released in public. There are two ways of security. There is the security by putting everything in public, which I'm a strong proponent of. Organizationally, we are forced to go into security by obscurity a little bit, and there are reasons why we had to do it. But keeping that aside, please don't beat me up on that on YouTube. Uh, but that's the only component that is closed source. Everything else is public, and of course ROM, which you can't read. Um, so anything that you're doing on the main Cortex ARM, all public, all open source. Anything that you're doing on the Cortex R, other than the ROM pieces, is public and open source, except for the device management firmware, which TI maintains as its own tree. Someday, maybe we might run Zephyr on it. But there are some pieces that come into play. Beyond the ROM that starts off, there are two major pieces that come in. One is the TI foundational security piece. That provides security services for the entire SoC. He's like the king of the system. And then there is the device manager functionality. Now that guy is supposed to help you with the mundane stuff like switching on the clock or enable a device or give me a DMA channel. And most of our processors are heterogeneous systems. So instead of one processor trying to figure out how do I talk to a specific operating system running on a second processor, why not centralize all of this into the device management function, which is what we did. And that guy is running on the same boot R5 on AM62 context that was also running your R5 SPL. So until device management function gets online, you don't get the generic functionality that the base SPL gives you. SPL stands for?
Secondary primary load.
Right. Good job. It's a scheme. So the first bootloader in the system, the first piece of software that runs is the ROM. So people usually call the next stage of bootloader as the secondary bootloader. So the TI terminology is SB, B as in beta, L, secondary bootloader. The U-boot terminology for the same function is SP, P as in Peter, L. So that's what we are looking here. We are purely looking from a U-boot. Of course, we are looking at the U-boot documentation here. There are multiple authentication steps that is involved. A lot of people want simplicity, they want security and simplicity, but there is always a trade-off. If you want security, you have to authenticate your binary, which is a standard that we have taken. You will have to spend some effort in bypassing security, but then you are doing that consciously. So it looks a little complex, but it is done for a reason that way. So the initial TI boot 3.bin, which is the file name that comes out of SD card, we'll go into how the structure looks like, contains the TIFS, which is the foundational security firmware. It also needs some sort of a configuration file telling it how to configure for this SoC. And this is the big work that Neha did. That configuration is now part of U-boot itself. It's the binman framework. And you can describe all the configuration parameters as part of YAML properties and device tree, etc. Pretty cool stuff. But all that does is to tell TIFS how to operate on this specific board. So you can customize it based on your board needs. Which resources are partitioned. For example, you want to give a lot of writes to the M4 on AM62. You can do that. And you can take away writes for certain peripherals out of the A53 that we have on AM62. So you can play with both sides of it. So all that stuff happens in the config data. Our default config data allows both the Cortex A and the Cortex M to take any resource it wants, provided it's first come, first serve, essentially. That's what the default configuration is. But it doesn't need to be that way. You can strictly control which resources go to who as well. Next level. After that guy comes up, TIFS starts running. Now you have security services. So the secure ROM disappears from the picture. Now it's a pure firmware game. And ROM, as a rule, we try to keep it as minimal as possible. The reason is more complexity you add in ROM and you have a bug, your product is out there in the field, you can't even take that back. Instead, you want to put complexity in a piece of firmware that you can upgrade over the air. So when SPL starts up, so TIFS is running on the side and this ROM gives a jump across to the R5 SPL. First thing it does is to get DDR. And unfortunately, the DDR configuration is a little bit complex, but no biggie. Then it jumps to another piece called a tispl.bin, which it loads up. Tispl.bin is essentially all the pieces you see on the right side, which is the Cortex A pieces. And then it loads the device management firmware, and it says go Cortex A, and it does a jump to the device management. So obviously, as you can see, there's a bit of a timing window here where TFA might need services from device management, and we have figured out how to make this stuff actually work. There's a bit of handshake, blah blah blah, to get the timing right. After that, the Cortex R essentially becomes a device management function. Now on AM62, I'll give a warning. There's a lot of people thinking that, oh, there is a Cortex R sitting there. Let me make it do 20 other things. Yes, you can, but you have to be careful. If the device management function fails, everything on the ARM or M4 will stop functioning, because this is the guy who is managing the entire system. So be careful. As long if you can avoid it, don't touch the R5 on AM62. Cortex A side, the TFA starts up, which stands for Trusted Firmware Cortex A. That's the guy who runs in ARM terminology in exception level 3, which is the highest security level of Cortex A. That gives that, in the old world, we used to call that as trust zone as a single world. In ARM v8 generation, trust zone has split into multiple worlds. There is what we call as a monitor or EL3 level. There's a EL1 running its own operating system. Yes, we have another operating system that you don't know about. It's called Opti. And there are trusted applications, which are secure applications running on top of that Opti operating system. All that stuff has to get started up first, because you need secure services for Linux as well, and U-boot for that matter. So TFA Opti gets started. The next guy to start up is Cortex A SPL. Why do we do this? Because if we load the entire U-boot, it's big. People like to add features to U-boot all the time. So we try to keep something minimal that can load U-boot image to the DDR and get started, because early in the process you're limited by SRAM quite a bit. So you don't want to do very fun stuff here. But you can bypass this if you like. You can just have SPL alone and make the SPL jump across to the Linux operating system if you choose to do it so. I haven't put the Linux OS boot process here, but that's standard U-boot branch to Linux flow. But this is kind of the overall system. Depending on the device, you may even have the option, sitting on the U-boot shell, to start up the M4. Ta-da! Even on some other processors, we can even start up stuff like the PRU, which is another story of its own. Long story short, it's not that straightforward when you look at it in the earlier picture. Like straight line flow is not exactly what happens inside each of these firmware. So as we come down, the actual build process by itself is a little bit complicated. There are multiple stages of builds that you need to do. You have to build trusted firmware with specific properties. You have to build Opti with specific options. And then you have to build the R5 and the A53 side of U-boot. Okay? Obviously, there is a specific pattern that you can use for building all these 4-step process. But we try to make it easy in U-boot by giving you pre-programmable variables that you can use to build all this stuff. Now, if this is too complex for you guys, well, we have an answer. Well, I found it complex, so I was feeling very lazy, so I wrote what I call as the K3 upstream boot build. Ta-da! What this guy does is to do everything that you just saw in 2 steps. So ignore all the crap that you have over here, just clone this repository, and you do the command called git sync, which will download all the U-boot stuff and all the various firmware pieces that you need. And you can do my board def config and make, and you're done. Obviously, assuming that you have your compilers and all that things installed. And there are some overrides, etc. And it will happily put all the required binaries in a folder to deploy directly out. Yay! So that would be your very first step, which is to do a git clone of this repository before we get started. All right. I'm going to start the clone and I'll go through the steps. Since the clone takes a few minutes, okay, let's use HTTPS. We will take a small pause. Oh, wait, I've already cloned it. How come I forgot about that? Wait, I developed this thing, didn't I? So, we have that cloned right here. Okay, as you can see, um, I like this command, but be careful when you guys don't know exactly what you do. But when you clone, you come to this kind of view. You got the ARM Trusted Firmware config, OptiOS, TI Linux firmware, and U-boot. There'll be these folders in place. So the first command that you do is make git sync. What it does, in effect, is to pull in all the sub git modules down. For folks who like to run your own git sync command for each of the remotes, go ahead, do it. I am too lazy, so I like a single command to clone everything down. In my case, I've already done this. Okay, so I'm going to skip the step where I'm doing make git sync. So if you do a configs folder, you will see there are many config files. If you're familiar with Linux configurations, you're in the happy land here. So in our case, we are going to build for AM62S. So make AM62S def config make, and that's all that we need. I'm just trying to make sure. Okay, I'm just trying to make sure that I have everything in right. Right now, I was working on something for optimizing. So how about we switch to the master branch? Will that work? Should work. Checkout is usually a good command. Git pull. Sorry. Okay. Make -j nproc. So I probably didn't do that command yet. So make AM62X GP all, or I could use HSFS, which is the board that I have right now. I was having. Make -j nproc. Okay, here we go. So all the steps that we saw documented is running in the background. It has built Opti, it has built TFA, it is building U-boot, putting all the binaries with binman together in the right format, etc. And the image is created here. So if you look at deploy folder, you'll see there are 3 files, and this is the end result of all the documentation that we just wrote. tiboot3.bin, which is the initial startup image, tispl.bin, which is the initial startup images for the A53, and uboot.img, which is the uboot bootloader. It's that simple. Now, if you're looking for in terms of what is the structure of each of those images, hey, you are in luck. We have documented that as well. And how it looks like on the memory map, blah, 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 dip switches, settings, everything is in the uboot documentation, just for you. All right, now we come to the more interesting problem. How and what in God's name is device tree? So for folks who have worked on Linux, git branch. All right, I am on 6.5 RC1. All right, yeah, ls arch ARM64 boot dts ti. Ta-da! This is called device tree. I can talk a lot about device tree, but in effect, all device tree is the hardware description. Period. There are 2 parts of this. Hardware is a very vague term, so we try to make more sense out of it. So there is the SoC, which is the processor like AM62, and then there is the board. Both are hardware, and the one that actually gets created is a combination of this 2, called the device tree blob, DTB. So if there are different, if I were to just do grep AM62, there's a heck of a lot of files that comes into play here. There are different boards, blah blah blah, etc., which is in the Arch ARM64 DTS-TI folder, right? So far so good, right? Here's the bad news. CD U-boot, LS, Arch, ARM, DTS. Oh my goodness, how many files are here? All the device tree files in U-boot is located in one folder. 2678 files as of right now on U-boot master branch is the exact same file that Linux kernel also has. Now, what do you do when you're doing a board port? Typically, when you're creating a new board, the first thing that you do is you would start creating a device tree. Once you have your U-boot device tree working, you would take that device tree and put it in Linux kernel and try to bring the Linux kernel up, because device tree is the same. It's hardware description. We don't use an entirely different language in U-boot device tree compared to Linux kernel device tree. The problem starts happening because when you're trying to create a board device tree, you use the SOC device tree as the include file. Let's take a simple board here. 62SK is a good one, I guess. Maybe. So let's look at this guy. Not exactly a trivial device tree file, but this is our TI's SK platform, starter kit platform. This is the line that is the most troublesome of all. We wish everything was in a perfect world where we could get all the device trees updated in one shot and upstream is perfect, but that is not the reality. It happens in stages over multiple months. So AM625.device tree includes the main and multiple other DTSI files onto which new nodes come along over many months in kernel device tree. Now, when you enable a new peripheral for whatever reason, a new audio codec or USB support, for example, you run into a problem. You can enable this in Linux kernel, no brainer, but when you try to enable the same peripheral on U-boot, now you have to ensure that, like for example, the main I2C node is available in kernel and U-boot. These two are entirely two different software projects. They do not share a single Git repository where all the device trees are maintained. Instead, they are in two different Git repositories. So if you were to have main I2C0 as a device tree node, whose name changed in kernel but not changed in U-boot, you can't reuse the same device tree. You'll have to do your work twice, one for U-boot separately and again for Linux kernel. And this has been a major pain in the butt because there are bug fixes that happen in Linux kernel. People forget to do the same bug fixes in U-boot, and all kind of mix-up. Sometimes you see fixes happen in U-boot, but not available on the Linux kernel, and vice versa. So we've been going nuts trying to keep the system alive over the many years that we have. So the answer was very straightforward. How about we take these files that that was a VI command. ls, right? And copy them over here. Why can't we do this?
I don't know, size?
Nope. The trouble here is that you notice there are some extra files here.
Mm-hmm.
uboot.dtsi, r5sk.dtsi, etc. These are some extra files that we have to introduce because uboot does something little extra which is different from what kernel is doing. So those device tree files have also to be updated when the kernel device tree is pulled in. That's all that major exercise is all about. Okay, so we have been working pretty much trying to reduce, if I were to use the SK, AM62 SK, right? So if you look at master branch, right, of course, I'm in the wrong folder. Arch, ARM, DTS. It does, okay, this looks very similar to what you have over here. If I were to take a diff between this, and let me find the real path of that. Kernel versus U-boot. It's exactly the same right now. Okay, but there are different files that can be different. If I were to take 625, why? Arch, ARM, DTS. Where's the slash? There we go. So this has a lot of nodes that are put in place. I think he merged my, okay, apparently he did merge my changes. So sorry, I was trying to demonstrate that how we do the porting, and I did not realize that he has already merged my patches. So I'm going to reset and go one commit low. Actually, this is the cleaned up version. This is how it should look like. But we are jumping ahead. You should see what happened. Oh, actually, I can do a git log minus p. That's going to be bad. Okay, I'm going to jump one commit before that. Alright, so I've reset the thing. Now let's look at the same file. This is how it used to look like before. Okay, it was defining the timers. It was defining all the nodes. Now this is one of the better files. Okay, there are much worse files out there, but let's look at a good file. You'll see that there's a lot of duplication that happened. Like the timer, for example, we managed to get timer support in upstream kernel, but U-boot did not have it at this stage. So when you start the entire intent here is to first take all the kernel device tree files, not all of them, at least the ones that are there on the tree in U-boot, take those specific files from kernel tree and copy them over to the U-boot. Step number one, right? Step number two is to do the cleanup, which is the updates that you have to do onto these files, the uboot.dtsi, to remove. So now you'll have duplication. Like the timer came into kernel.org, right? So if I were to do git log of 62 main.dtsi, you will see, for example, secure proxy was something I added in upstream kernel. So when I did the sync, secure proxy came along with it.
Yep.
Okay. Timer, in the meanwhile, watchdog timer, etc. also got added in upstream kernel. Timer probably happened early on. See, this is the kind of fixes that I was telling you about. The OTAP delay and ITAP delay is MMC fixes. We never had it in U-boot. So most of the U-boot boards were kind of broken for MMC. At least on AM62. Until today morning, when he merged it.
I saw that J7200 at least had a thermal DTSI added to Linux in April. Is that something that would be ported
That
back?
will come back.
Yeah.
Everything moves in from kernel for that SOC. And this is the one that I was telling you. So Tony added this on November of last year, but we never synchronized this back into U-boot yet. So the timers were not there when we did the U-boot DTSI first time. So we had to define our own timer because R5SPL cannot work without a timer. So we had to give it a timer. So we defined our own node for the timer. But this added all the timers in one shot. So when we inherit this, you don't define it again. You delete this off and you use what's coming out of the DTSI directly. So this is the cleanup activity that we have to do. And CP switch, for example. We hacked around CP switch for quite some time. And Maxim Rippert from Red Hat last week decided he's going to help clean that up. Yay!
Nice.
So he and Roger Calderos, who works for us, They both collaborated and figured out how to get rid of this node entirely. So if I do a git pull and we look at the same file, ta-da! Look at that. All the CP switch hack that we had, gone.
Nice.
We still have a little bit of a hack around OSPI, which is a different problem. But the next thing we are trying to attack is this one. If we can get this property in Linux kernel, we don't need this file anymore.
That's one thing I was going to ask.
That's in the next cycle.
Because is that the main reason for the U-boot DTSI file?
Exactly, just
literally
for this stupid property.
Okay.
That's how it is supposed to be. Just to maintain this little property.
Yeah, I kept
Ideally
looking
speaking,
and I was like, what's the purpose of this?
yeah, so it tells U-boot at what stage. It does two things. The full device tree blob is so big, right? It has
Yeah.
display, video, everything on a GPU, all crap. But U-boot doesn't need that. So two projects happened simultaneously. There was a project called a Lopper under the OpenAM umbrella, which takes a device tree, a system device tree, and lops it down to just the relevant pieces that is interesting for a specific processor. So you have a common description and you can take a subset of that and even change the view of how these peripherals look like. Because depending on which processor you're in, your address view changes as well. So you can do that mod by using Lopper. And there is this entire project called as system device tree around it. Zephyr is an operating system that uses system device tree. In parallel, the U-boot guys developed their own solution. They said, we are faced with the same problem, but we are going to take a different approach of adding a property which will tell us which nodes need to be taken and which nodes does not need to be taken. So they attacked a very narrow problem. Whether we like it or not, okay, no judgments here, people. This is judgment-free zone. That property is now mainline. So those properties are now merged as part of DT bindings and they are formal properties now. So the system device tree guys are still trying to integrate with the kernel device tree. They went off their own on their fork. The kernel device tree has been evolving on its own. There are at least two projects that use kernel device tree, U-boot and kernel. One of my projects that I'm thinking of working on is to integrate that with Zephyr and integrate that with system device tree. Because kernel device tree is very, very rich from that perspective, and it is very much more well organized compared to what I've seen in system device tree. Anyway, so that's a future looking project, but the entire idea is the same problem. A huge hardware description, but the stuff that is relevant to me alone is a subset of it. So how do I find who is that subset? And U-boot uses this property to trim things down. The way that we are using is not proper yet, because you need certain properties before the DDR is active and certain other properties after the DDR is active. Like for example, you need USB. Why would you waste your time and SRAM memory initializing USB if you can initialize USB after DDR is off when you have a larger stack and malloc space available? We can optimize this much better. But stage number one is to get rid of these properties from uboot.dtsi, which means we are having a kernel patch coming, people. Please do review and hack it for me. But that's the only thing that we are doing. The other thing that we are doing is to disabling certain ports, like the CP switch port number 2 is getting disabled. That's a conscious decision we took because we don't want people to be confused as to which network port to get their DSCP working on. If your ideal answer is, why don't you enable it on both? But there are a little more nuances involved in that. Long story short, our CP switch and MDIO driver in U-boot upstream requires a bit of more work. So, I said it. Now, beat me up about that. The other stuff that we do is that the clock frequency setting, right? We have, because nothing has started up yet. It is early R5 bootloader. It needs to know what's my frequency. The kernel device tree has device manager to tell him, hey, your frequency is so-and-so. But SPL has no device manager to tell him that. In fact, he doesn't even know what the clock frequency is because without that, he can't even compute what the rest of the clock tree looks like. That's the only other instance where we are trying to reduce things out. So I'm trying to get this to 0, which is my next goal for the next U-boot window. But I need to get this into kernel first. Before the sync back, the property is already there in the soc.dtsi and board.dtsi. So I no longer need that in u-boot.dtsi. So one more cleanup cycle coming up.
So you can remove the entire file.
Right. So our first phase that we are trying to achieve in this 2023.10 U-boot window that we have is to get the kernel device tree in, clean up the u-boot.dtsi so that all the extra cruft that we had added, we clean that up so that only minimal, this is exactly how it should look like. Now, to be able to do that, there are two views of the same problem. This is the A53 SPL view. There is a similar view that exists on the R5 side. And this has been rather painful. So we have an R5.dts as well. The way it was done before, and this is a harder one to solve because the address map view changes, the kernel device tree, and this is the problem that Zephyr faces, right? When they use the system device tree, they're looking at it from a R5 perspective, A72 perspective, or A53 perspective. And the perspective is very different. And when the R5 SPL starts up, it has its own set of challenges, primarily around this thing. The way that it looks as A53 and the TIFS and DM does not exist is different from what every other component will look at the system once the DM is active. So this is a little more complex, but the stuff that we could have gotten rid of, like the secure proxy main and that kind of hardware, small pieces, those are in upstream kernel now. So that it used to describe that in the R5 device tree. The other thing that some of the board guys have done, and I think, I'm not sure which of the Jacinto boards have that, is that they decided that they will rewrite the board file from scratch in R5.dts. So how much DDR you have is described in R5.dts and on the A53, which is the default board.dts. And I'm like, why would you want to do that? Why don't you just, there's this nice C language thingy called hash include. It works like a charm, right? So that's what I did. So if you look at this include, it starts with the board.dts, puts the DDR DTSI in, then these two lines introduce the DDR configuration, which is only needed for the R5. There's no point in increasing our DTB size. And then applies the uboot.dtsi because many of those properties that we spoke about is common. I need MMC, I need DMA. Those are all common stuff. So I can get those nodes coming in from uboot.dtsi because both A53 and R5 need the same properties. And then on top of that, I can add the deltas. It keeps everything clean and much more logical for me. Today, depending on the platform you look at it, you see very, very different views. And that's part of the cleanup that we need to do for this window.
Yeah.
Okay? And that is, if it is ridiculously bad, it's going to be a very hard thing to do. Because now you have to compare node by node by node by node by node. Because everything is duplicated.
That's a little bit of the problem I'm coming across is because it's not just that U-boot's missing some of the patches from upstream. It's that U-boot has some patches that is missing in upstream, and you're not sure
which one to pick.
Yeah.
So that we have resolved in kernel. Right now, if you see a conflict, trust the kernel device tree. So that we have resolved. We did see that there were differences. Took all those node, like pin muxes. Yeah. One would pull it as pin input high, the other one will be just pin input. What should I pick? And then we walked down detail by detail by detail, and we said, okay, pin input is exactly what we need. What we added as pin input high was actually a copy-paste mistake. Not a good idea. But that's the major cleanup that we are going through right now. R5, unfortunately, also needs this kind of a hack. Why? Because OSPI is a very good example where R5 is a 32-bit processor. OSPI is in the 64-bit address space beyond 32-bit access. So we have this little module called as RAT. Not the RAT, the little one with the little whiskers. Region Address Translation, which is a very, very poor man's way of doing an MMU. It takes a virtual address and maps it to a physical address. That's all it does. It doesn't have an MMU table. It just has regions. That is the TI implementation. So we put that thing in front of R5 and we said, okay, for all those addresses in the 64-bit address space that you can't reach out, you'll map those addresses using a quote-unquote virtual address inside R5. That's a reserved address range that we use. So that's what this does. This uses that remapped address,
Okay.
predefined remap address. So it kind of tries, it's not perfect. What I would rather have done was to describe the RAT and the OSPI address and do the mapping inside SPL. But SPL also has the biggest challenge, boot time. We want it to boot fast, right? So we can't keep doing all the magical stuff we do in Linux kernel either. But as you can see, there are some properties here which probably can also disappear. But that's what this entire thing is. So the steps, if I were to go one by one, take uboot master, the very latest step, go to Linux kernel and check out 6.5 RC1, not the latest, not the Linux Next, RC1 tag.
That was one of my questions. Because I saw you mention in a patch
Yes.
that you had to be very careful.
Yeah, because I'm trying to make sure that everybody is on the same baseline. Because what you don't want is people coming along, because many of these vendors have multiple products on TI. You don't want them to come along and say, oh, if it is this SOC, it is 6.4 kernel. But if it is this SOC, it is 6.5 kernel. Now they're confused, right? Why confuse them? We are all at the same level. That's all this is. Unfortunately, I understand it's a lot of janitor work. Sorry. It's a lot of SD card booting and switching around and trying new boards, one after the other.
Good learning opportunity.
It is. It is. That's all I had, and thank you for watching, folks.